Welcome to this third part of this lecture based on unitary operators. So, in this lecture, I am going to talk about the time evolution of expectation value. So, the time evolution of expectation value of an operator A means we are interested to find derivative of this expectation value of this operator. Now let us define expectation value of the operator, and expectation value of operator is defined in this way. Now let us calculate its derivative. If I try to calculate its derivative, then how it will become this is equal to d upon dt, right? So let me call it as equation number 1, and let me try to find out its derivative. So first of all, I have to take the partial derivative of psi t factor, and the rest of the terms are multiplied as it is, plus this psi t remain as it is, then differential of about the partial derivative of the operator, and this term will remain as it is, this third term, plus psi t into a operator, this remain as it is, and curly psi t we have to take its derivative, right? So this is another thing which we have to take care. So it can be written as curly psi t over curly t, and this A operator psi t, right? This part I have written here, and then I will write down this part now with it, plus psi t A operator, and this, and curly psi t over curly t, and this I will put in the last, and in the earlier lecture, as we know that, as we have defined in the earlier lectures, that this curly over curly t psi t, this is equal to minus iota over h cross h psi t, and curly over curly t psi t, this we have defined as iota over h cross this psi t, this is h operator, right? So if we will use these two values from here in this part, then this equation can be written as Let me write down it as this, and here it's iota by h cross with it and iota by h cross. If I put their values here, and then iota by h cross can be taken outside, and it is psi t, it is h operator, a operator, psi t, right, plus psi t, and this is a operator minus iota by h cross, h operator, psi t. That's what we're using here, and this I have taken outside iota by h cross is because of these two terms, and plus psi t curly a by curly t into psi t. So what I can do now, they can put together, they can also put together. So sorry, there is some mistake. This is not common to all, right? This is not common to both. Yeah, it will remain as it is. Then it is equal to, now iota by h cross can be written as minus 1 over iota h cross, because 1 over iota is minus iota. I use this identity here, and now psi t can be taken here. Here it is HA, and from here it is AH. So minus AH will be there, and here I can put this towards that side because it is with this term and this term and this also, right? So I will express it in this way, plus psi t curly a by curly t into psi t. So it can be written as it is HA. So if I multiply with minus sign here, then their sign will change, or it will be here and here. So it is 1 over iota h cross psi t. It is AH minus HA plus psi t curly a over curly t into psi t. So therefore I can write down it as d upon dt of expectation value of operator A is equal to 1 over iota h cross. It is psi t, it is a h, its commutator, plus psi t curly a operator over curly t and psi t. So now that means this is the expectation value of this operator and this is the expectation value of this one. So this can be expressed as a d over dt of expectation value of operator A is equal to 1 over iota h cross AH, its commutator and its expectation value, plus curly a by curly t and its expectation value. Now let us consider one more thing, that if A does not explicitly depend upon time, that means curly ay curly t must be equal to 0. So if this is so, then this above equation will become dy dt of expectation value of a operator is 1 over iota h cross, it is a h expectation value of its commutator. Now if a h both commute, then we can say that dy dt, its expectation value will be equal to 0. In other words, we can say that this is a constant of motion. Thus, if we summarize this result, thus a operator is said to be constant of motion, and thus expectation value of an operator that does not depend on time, that does not depend on time and commute with Hamiltonian, is constant of motion. Commute with Hamiltonian is constant of motion. Now, next, let us discuss a very important result. Since we know that psi t is equal to utt naught, and this important result is regarding the property of this unitary operator. And let t is equal to t1 and t naught is equal to 0, then I can write down as psi t1, it can be written as ut1 psi naught psi 0, and similarly I can write for another time t2, psi t2 must be equal to ut2 and psi 0. Now the probability is conserved. If probability is conserved, then one can write down as psi 0, its scalar product is equal to psi t1 and psi t1. So keeping this in mind, let us try to calculate that psi t1 plus t2, this is the initial time and this is the later time t2, so it can be written as ut2 into psi t1, right? But this psi t1 is related to psi 0, so it can be written as ut1 and psi 0. So if I do this, but this psi t1 plus t2, it can be written as ut1 plus t2 and psi 0 also. So if I compare these two equations A and B, then one can write down as ut1 plus t2 is equal to ut1 plus ut1 into ut2. So this is a very important result which we have to keep in mind. Then next is a exponential form of operator. Exponential form of unitary operator as we know that u inverse, if u inverse is equal to u dagger, which implies u dagger is equal to identity operator, then we can say that it is a unitary operator. Also we studied that determinant of u, we have studied this in lecture 1.3. in the last part of the lecture describe these properties. Determinant of u square is equal to 1, and this suggests that if determinant of u is equal to 1, this suggests that determinant of u is equal to exponential of iota theta, and determinant of u dagger, it can be written as exponential of minus iota theta. So this suggests that something can be written in the form of exponential. So keeping all these things in mind, because this is for the determinant, so for matrix which is unitary, then u can be expressed as e raised to power iota epsilon g. So now let us see what should be the values of what are the properties of now we have to see that what are the properties of epsilon and g for u to be unitary. Let us have a look at that. So since we know that from earlier mathematics that f of a operator, function of a operator, then it is nothing but f star and a dagger. So now consider u dagger, it is equal to e raised to power iota epsilon g, and whole dagger, it is equal to exponential minus iota epsilon g dagger. Then this u inverse can be written as e raised to power iota epsilon g inverse, and it can be written as minus epsilon g, right? So for u to be unitary, these two must be equal. These two equations must be equal. So this is possible if means u dagger is equal to u inverse. This is possible. This if epsilon is real and g dagger is equal to g, right? So that means g must be Hermitian, right? So g must be Hermitian. So that means if any operator can be written in this form, then is said to be unitary if epsilon is real and g is Hermitian. And this g is basically known as generator. This g is known as generator of this unitary operator. right? So this is a very interesting way to look at the unitary operator in terms of exponential. So with this lecture is finished. So in the next lecture, I will talk about infinite simile unitary transformations and finite unitary transformations. So thanks for watching this lecture.